All right, so we're going to start off with a little bit of a geometry review. And there's a couple things that you know already. You know the Pythagorean theorem, a squared plus b squared equals c squared. C is the hypotenuse of the right triangle, a and b are the legs. You might remember the midpoint formula, that if you have a segment that's graphed on a grid of some sort, and you have two endpoints, and we're going to represent them as x1, y1, and x2, y2, that the midpoint of that segment is basically the average of the coordinates. So you add up the two x values, divide them by 2. That's the x value, the midpoint, and the same with the y value. So there's some things that you know. We did geometry in two-dimensional space. Some of the geometry we're going to do this year is in three-dimensional space. And we're going to kind of model investigation number 1, which is on page 468 in your textbook. So if you have that handy, you can follow along a little bit there. So we're going to draw a cube. You might want to draw the cube first. And we're going to put it on the x, y, z plane. So you know the x and y axis from a two-dimensional plane. So x, y, z would be the three-dimensional plane. So this ray is going to be the x-axis. Then the y-axis is going to come along here through point C. The z-axis is going to go up that way through point D, so we have three-dimensional space here. And we're going to say that OA has a length of 4, and it's a cube, so that means all the sides have a length of 4. So when we write and we also just talk about the origin a little bit too. So the origin, we'll put point O there, and its coordinates are 0, 0, 0. So we're just going to add a third coordinate, and that's going to be our z value. So this is our x, that's our y, and that's our z. So that's why if OA has a length of 4, and if it's a cube, that point A has the coordinates 4, 0, 0. Notice that you go 4 along the x-axis, but you're not going any distance in the y direction or the z direction. They're both zeros. Notice then point B is at 4, 4, 0. So you're going to go out 4 units in green here to point A along the x-axis, and then you'll go out 4 in the y direction. And you're not going up, so your z value is 0. And then point F is at 4, 4, 4, because, and we'll trace that in green, you go 4 in the x direction, this is red, 4 in the y direction, and now we're going up 4 in the z direction. So that's where point F is at 4, 4, 4. So take a moment and see if you can find some other coordinates. If you want to stop the video here, you can, and then pick up on it a little bit. That would be great. So point C. Point C looks like it's along the y-axis. So point C's coordinates are going to be 0, 4, 0. Point D is on the z-axis. Its x and y values are 0, so it's at 0, 0, 4. If you look at point E, you're going 4 along the x-axis. You're not going in any direction on the y-axis, but you're going up 4 on the z-axis. So point E is at 0. Oops, not at 0, it's at 4. X is 4, y is 0, z is 4. So we're at 4, 0, 4. And then to get out to point G, it looks like we are not going any direction in the x-axis, but the y-axis, we're going over 4, and the z-axis, we're going up 4. So we'll call point G 0, 4, 4. So you should be okay at finding coordinates in a three-dimensional plane. So let's talk about finding the length of a segment now, the length of segment OB. If you want to kind of figure it out on your own a little bit, and the next one too, pause the video. If not, keep following along. So notice that OB and OA and AB make a triangle. They make a right triangle. So OA is 4 and OB is 4. So we can do our Pythagorean theorem and say OA squared plus AB squared equals OB squared. So we substitute our numbers in. 4 squared plus 4 squared equals c squared. 16 plus 16 is 32. So the length of OB is the square root of 32. Pretty neat. Now let's talk about finding the length of OF. Try it out a little bit. It's a little interesting. So if we're going to find the length of OF, notice that OF goes from one corner of the box to its opposite corner. It is also part of a right triangle. So if we wanted to do the Pythagorean theorem again, we could say that the square of OB plus the square of BF is equal to the square of the length of OF, another Pythagorean theorem. And we know OB's length is the square root of 32, so we can do this. BF has a length of 4. And let's evaluate. When we square the square root of 32, we just get 32. So this becomes 32 plus 16 equals the square of OF. So OF equals the square root of 48. Very nice. Now, did you notice something as well? Did you notice that the length of OB is actually equal to that distance there? So we could kind of almost do a super Pythagorean theorem here. We could do like a three-dimensional Pythagorean theorem. So that's pretty neat. We could have done, let's see, we could have said like OA squared plus AB squared plus BF squared equals OF squared. And what you might remember from last year as well, or from your geometry class, that when you did the distance formula is really a Pythagorean theorem. So if you take the square root of both sides of this, we're going to get that segment OF equals the big old square root of all of that stuff. Okay, so that's going to lead us into some three-dimensional geometry here. Check it out. We can do a three-dimensional midpoint formula. Again, it's just the average of all three coordinates. That's all it is. Good stuff there. And like we did as well with the distance formula, remember the distance between those points? It does come from like the Pythagorean theorem. So I'll start by doing this. I'll do like a big old Pythagorean theorem where we do like x2 minus x1 and square it. Remember, if we subtract those lengths or those coordinates, that gives us the distance between the points. It doesn't really matter the order you subtract them in. And then if we take the square root of both sides, I'm going to be lazy, and I'm just going to say that I have the distance here and take the square root of all that. So now we have like a three-dimensional distance formula too. Pretty cool. Nice, nice, nice. Hey, one quick thing about notation in geometry. We said that the segment you see on the right, that line segment with the endpoints A and B, we wrote it with the little bar on top. This is what we did in geometry. Just notation-wise, in IB, we put square brackets around it. So we're going to try to make our notation that way for you. And if you wanted to practice finding some distances and some midpoints of segments in three-dimensional space, I would urge you to take a look at example 1 on page 469. So we're going to keep moving a little bit. Let's talk about some three-dimensional shapes like pyramids, cones, and spheres, and hemispheres. Again, geometry review, you've seen a lot of these things. The one thing that I do want to point out to you is the pyramid and in the cone, in just some of the vocabulary of it, is the height of the pyramid or the height of the cone is the distance from the vertex perpendicular to the base. When we say the height of the pyramid or the height of the cone, we talk about that distance, that segment that I drew in red is the height. We also talk about the slant height. The slant height is the one that's along the slanted side, if you will. It's along the face of the pyramid. I drew those in green. So if you consider this piece to be a solid figure, then you can probably more accurately measure the slant height as opposed to getting onto the inside of it and finding the height. And last year you did a lot of work, or I say last year, in geometry, you did a lot of work with volume. You found the volumes of pyramids and cones and spheres and hemispheres. You know those formulas. If not, I will give you those formulas. One thing that we didn't hit in geometry, though, was surface area. So if you think about the area of a surface, it's really the area of all the faces and the base together. I'm going to go back one page for a moment and take a look at this pyramid. So in the pyramid here on the left, the surface area we want to find is the area of a square base plus the area of 4 triangle faces. We want to find the area of all the sides of it and add them up. So when we do that in a cone, it's a little tricky, because what we know is that r is the radius of the base of the cone, and L is the slant height of the cone. You may remember from geometry days that the distance around the cone is the circumference, and circumference is 2 pi times the radius. So if we were to cut along that slant height and spread the cone out, it wouldn't make a whole circle. Okay, it wouldn't make a whole circle on that. But the shape that we would make is like a fan sort of shape, where L is still the slant height, and 2 pi r is the circumference of the base. And what we could do is we could take these little triangles here, take that triangle, see if we can do a little smartboard magic. Take that triangle there, I'm choosing that one, because what I can do is I can take this and I can pull it apart, and I can take that one and flip it over, and I can put those next to each other like that. They kind of line up. There you go, there's what we're going to do. And what we can do is we can rearrange them to make a sort of like a parallelogram-ish rectangle. So the area of this parallelogram, or this rectangle, is base times height. So this area is going to be the base times the height, pi RL. So that's the area of the surface part of the cone. But don't forget, you got to take the area of the base too. So the surface area of a cone is going to be the area of the base, pi r squared, plus the area of the side of the cone, the lateral side of the cone, we call that. And hey, maybe you can use your algebra skills and do a little bit of factoring there. Oh, that would be beautiful. Nice little relationship there if you could do that. Cool. So that's the surface area of a cone. How would you find the surface area of a sphere? Oh boy. Well, here's what we're going to do. We're going to visualize that a sphere has a bunch of tiny shapes that cover it, kind of like a soccer ball. And pretend that the surface area then is the area of all of those things added together. Furthermore, let's say that those polygons are the bases of pyramids. So pretend this is a pyramid with a pentagon base right there that sticks into the center of the cone. So the height is always going to be the radius of the cone. And think about a whole bunch of those. So we call that like base number 1. And then there's another one over here, and it goes in like that. And that is base number 2 with that cone, or with that pyramid. And let's just say we can divide that surface area into 1,000 of those polygons. So the area of the first one is base 1, then base 2. Well, the surface area of the sphere is what those 1,000 areas add up to. Okay, but what are those 1,000 areas? I get you. Let's keep going. Remember that we found the volume of a pyramid by doing the base, the area of the base, times the height, divided by 3, or multiplied by a third. And remember, the height of each of these pyramids now is the radius of the sphere. So what we can do now is we can write the volume of the sphere as 1/3 times the area of the base of the first cone times the height. So this is the volume number 1. Then we're going to add it to volume 2, and so on, up to volume 1000. That's going to be the whole volume of the sphere. Cool. And I got some dots. What do all those dots mean? Oh, remember that we got the volume of a sphere, though, is 4/3 pi r cubed. So we're going to do a little bit of algebra here. We're going to take that volume in a minute. But again, factoring. Let's do some algebra. I'm going to factor the right side for a minute. Notice that they all have 1/3 in it. They all have an r in it. So I'm going to factor out 1/3 r, and what I'm left with is base number 1 plus base number 2 plus blah, 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 plus base number 1000. Cool. That's my volume of the sphere. But the volume of the sphere is also 4/3 pi r cubed. I don't want to write v over there. I'm going to plug in 4/3 pi r cubed for v. All right, where are we going with it? Check this out. I know the value in parentheses, b1 plus b2. That's the surface area of the sphere. So I'm going to rewrite this equation. I'm going to rewrite it like this. Here's my volume, 4/3 pi r cubed, and that's equal to 1/3 times r times the surface area. Now, let's solve this equation for S, for surface area. First of all, I see a 3 on both sides in the denominator. Those 3's cancel out. So now I'm left with 4 pi r cubed equals r times S. Well, if I divide both sides by r, that r cancels one of the 3 r's here and makes it r squared. So the surface area of a sphere is 4 pi r squared, which is pretty neat. It means that the surface area of a sphere is 4 times the area of the circle that you can make by cutting the sphere in half. Pretty neat stuff. Cool. Hey, there's now some good practice work that's ready for you. Have a blast.